Assalamualaikum. My name is Muhammad Nizam Nasir. So here we are from group 3, section 2. So we will discuss about lab number 2. The lab title is Flow over Instruments, Body and Boundary Layer Theory. My name is Muhammad Nizam Nasir, metric number MA19134. So for the abstract, we will try to prove Liouville parental boundary layer effect theorem in this second experiment. To begin, in the early year 1900, Liouville parental present the hypothesis that characterizes boundary layer effect, even though the general fluid equation had been known for a long time. Their solution failed to adequately capture observed flow effects such as wing stalling. Prandtl was the first to realize that the relative magnitude of the inertial and viscous force changes as you move away from the surface. He first developed a two-layer interactively coupled solution that accurately mimicked a variety of flow problems. When an item travels through a fluid, the particles around it are disturbed, and the particles closer to the surface cling to the surface. When particles just above the surface collide with particles adhering to the surface, the particles just above the surface slow down. These particles cause the flow above them to slow down. The further away one walk from an object surface, the less to form at the surface with velocity that varies from 0 at the surface to the free stream value further away. When this happens, the boundary layer is created. This boundary layer generates the aerodynamic force between the fluid and the object. The fluid primary aerodynamic force are drag and lift. Introduction. For the background, this study focused on the flow of water over submerged body. This station includes the following past object. When an object is submerged in moving water, the interaction between the object and the water causes it to submit to force. The force involved are drag force, lift force, shear force, and pressure force. Furthermore, flow past an object such as a circular cylinder produces a wave or vorticity due to shear in the boundary layer. The vorticity in the flow field combines to generate vortices on both sides of the cylinder, which are instant vorticity zones. A variety of phenomena influence the flow around the bodies. One of the most significant forces on the body is that exerted by fluid. These transmission lines, aircraft control surface, offshore structure, thermal well, engines, heat exchanger, marine cable, towed cable, drilling, and production. Research in petroleum production, mooring cable, two more structure, data structure, buoyancy, and spar hulls, pipelines, cable laying, member of jacket structure, and other hydrodynamic and hydroacoustic applications are just a few places where they can be found. So here, this is flow pattern pass of a cylinder. Furthermore, this study focuses on the way of flow behind the body shown in figure 1.1, which has been extensively studied due to their numerous practical applications and important in engineering area. Aside from that, the purpose of this study is to figure out what the drag coefficient, CD, and drag force are for various objects shaped at varying speed. So figure 1.2 is water flowing around the object. This is the object. As shown in figure 1.2, various parameters influence the flow weights, including size, shape, orientation, fluid speed, and fluid characteristics. The length of an object weight is controlled by its shape. Apart from that, the drag coefficient for item shape has an effect of the object. This study uses of a physical body to generate outcome depending on different shape. One feature of the experiment is the length of the wave created when water flow past the immense object. The purpose of the experiment is to figure out how much drag the immense object had. Experiments are conducted out at various flow rates for each different form of the object. Problem statement. Our lab session for this semester will be conducted online because of the COVID-19 pandemic, and the experiment measure was provided. Several practical scenarios are included in this experiment, including flow past body. When a fluid passes between two or more bodies, it creates an interaction between the bodies and the fluid. Flow past body, according to Su, is an essential topic because of their many technical applications and great flow physics, such as expression, reattachment, vortex seeding, and so on. Take for example, a bridge piers. Piers are the principal pillar on which a bridge superstructure is supported. The flow of water can be affected by the geometry of the piers. The piers will hinder the flow, resulting in pier vibration and structural failure. The flow rate is also affected by the shape of an object. Furthermore, regardless of the pier's shape, flow instruction within the channel is inescapable. Aside from that, the shape of an object has impact on its drag coefficient. Objective. The objective of this project are as follows: to investigate the relation between weight, length, and flow velocity for different immense object shape. To estimate the drag force exerted on immense object of different shape at different velocity. Scope of study. The flow past of or around immense body is more important in this investigation. The hydraulic laboratory was employed in this case. The open channel flow experiment facility was employed in the lab. The results for various shapes were calculated using three form objects. Circular, rectangular, and square things such as plastic pipes are among the shapes. The work complete in the experiment are as follows: to measure the length of the wave that arises when water is flowing past the immense object, to measure velocity and the head of water that occur when water flow past the immense object, to estimate the drag force at different flow velocity. Thank you.
Hi, I am Wan Abraham Wan Muhammad Sofi. My metric ID is MA19109. My topic is from chapter 2 about theory. This chapter will give a short summary of all important scientific research and knowledge related to future analysis involving flow over immense body and boundary layer theory. The first theory is boundary layer. The impact of the boundary layer of a plate subjected to longitudinal flow on two different surfaces, smooth and rough, and must be determined and validated in the study. The goal of this study is to compute the velocity profile in the boundary layer of a flat plate and compare the result to theoretical prediction. Front invent the boundary layer to better comprehend the flow of a slightly viscous fluid near a solid barrier. The boundary layer was the first to notice how the amplitude of inertial and viscous force are altered as we travel away from the surface. It proposed two-layer interactively connected technique that accurately mimics a variety of flow issues at first. The particles in the area are disrupted when an object moves through a fluid or when a fluid passes over an object. Particles are close to the surface, cling to the surface. The aerodynamic force of drag and lift are the two most potent when the particles just above the surface area collide with the particles stuck to the surface and they slow down. The flow above them is slowed by these particles. The more ones walk away from the item surface, the less collision are affected. This creates a thin layer of fluid near the surface in which the velocity changes from zero at the surface to the free stream value away from the surface. So this kind of phenomenon is called by a boundary layer. The next theory is flow over immersed bodies. Flow over bodies immersed in fluid when a solid body is completely submerged in a moving fluid and is held in its path. The body is subjected to some force or pressure when a body is propelled through a fluid at rest at a uniform velocity. The fluid provides a resistance to moving body, or the moving body must exert force to maintain its steady motion. The drag force is the name for the resistive force. There are horizontal and vertical force, with horizontal force representing drag and vertical force representing lift force perpendicular to the flow of direction. When a viscous fluid flows through a body, it creates a net force. When a viscous fluid flows through a solid body that is completely submerged in moving fluid, the body experiences a net force. The forces are separated into two categories, drag force and lift force. That's all for me. Thank you.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Harib Abdullah. ID number MA19202. Okay, for today I will discuss and share about the result and discussion for this lab. For experiment 1, we do the experiment about the flow pattern of symmetric aerofoil at different angle of attack, flow over immersed body. So we get the data from our lecturer. So we get the initial head equal to 137 mm, and we get the three type of angle, which is for angle 1, angle of attack 0 degree, angle of attack 30 degree, and the last one, angle of attack 45 degree. So the fan speed that we use from 12 to 19. Okay, for the first one, plot drag and lift force at various angle of attack for different speed. So our group just conduct the experiment and get the data, and for the calculation we use the formula for to get the FD. We use formula CD equal to drag force over dynamic head multiplied by area. So CD is a constant, which is 0.59. So when we put the data in this formula, we can get the FD for 0 degree, for 30 degree, and for 45 degree. Okay. After we calculate the data, we plot the graph. Based on the graph, as the fan speed increase, the drag force increase as well. Drag force of 0, 30, and 45 degree have very similar graph pattern, but we can see clearly that for 45 degree are very the highest. Okay, for the lift force, also we calculated by this formula, but for the CL, actually there are a typo. For the CL, for this calculation for lift force, we use constant 0.84. So when we get the data, we put into the formula and calculate, and we get the result. And we also make a graph, lift force versus fan speed graph. Okay, based on this graph, the lift force increase as the fin speed rise to. Lift force 0, 30, and 45 degree have very similar graph pattern, same like the drag force, but the lift force at 45 degree increase the most in comparison to 0 and 30 degrees. Okay, for number 2, sketch the streamline of the aerofoil that different inclination angle with separation and stagnation point clearly labeled. So we get the 3 type of angle attack, which is 0 degree, 30 degree, and 45 degree. Okay, for 0 degree, the flow of the air is like normal, which is have a separated point, and they have also the turbulent wake at the back. For the 30 degree, the airflow have separated point jump forward at the back of the aerofoil and have the turbulent. And for the 45 degree, separated flow region expand and make lift force, okay, which have a large turbulent wake, reduce lift, and large pressure drag. Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Harib Abdullah, ID number MA19202. Okay, for today I will discuss and share about the result and discussion for this lab. For experiment 1, we do the experiment about the flow pattern of symmetric aerofoil at different angle of attack, flow over immersed body. So we get the data from our lecturer. So we get the initial head equal to 137 mm, and we get the 3 type of angle, which is for angle 1, angle of attack 0 degree, angle of attack 30 degree, and the last one, angle of attack 45 degree. So the fan speed that we use from 12 to 19. Okay, for the first one, plot drag and lift force at various angle of attack for different speed. So our group just conduct the experiment and get the data, and for the calculation we use the formula for to get the FD. We use formula CD equal to drag force over dynamic head multiplied by area. So CD is a constant, which is 0.59. So when we put the data in this formula, we can get the FD for 0 degree, for 30 degree, and for 45 degree. Okay, after we calculate the data, we plot the graph. Based on the graph, as the fan speed increase, the drag force increase as well. Drag force of 0, 30, and 45 degree have very similar graph pattern, but we can see clearly that for 45 degree are very the highest. Okay, for the lift force, also we calculated by this formula, but for the CL, actually there are a typo. For the CL, for this calculation for lift force, we use constant 0.84. So when we get the data, we put into the formula and calculate, and we get the result. And we also make a graph, lift force versus fan speed graph. Okay, based on this graph, the lift force increase as the fin speed rise to. Lift force 0, 30, and 45 degree have very similar graph pattern, same like the drag force, but the lift force at 45 degree increase the most in comparison to 0 and 30 degrees. Okay, for number 2, sketch the streamline of the aerofoil that different inclination angle with separation and stagnation point clearly labeled. So we get the 3 type of angle attack, which is 0 degree, 30 degree, and 45 degree. Okay, for 0 degree, the flow of the air is like normal, which is have a separated point, and they have also the turbulent wake at the back. For the 30-degree, the airflow have separated point jump forward at below at the back of the aerofoil and have the turbulent. And for the 45-degree, separated flow region expand and make lift force, okay, which have a large turbulent wake, reduce lift and large pressure drag.
Assalamualaikum warahmatullahi wabarakatuh. And hi, my name is Muhammad Asrafik bin Arwin, metric number MA19126, and I will be presenting the result for experiment 2, rough and smooth surface plate. For the experiment 2A, smooth surface flat plate, the initial heat is 278 mm. The first plate distance in millimeter is counted by 0, 20, 40, 60, 80, 100, 122, and 140. Then the boundary layer thickness is 4, 8, 12, 16, 20, 24, 28, and 32. We find the heat in the table as stated in the table, and then we calculate the velocity using the formula V equal to rgh. Then we calculated the Reynolds number, R Reynolds equal to rho V L over mu, where rho is 1.184 kilogram per meter cube and mu is 1.849 times 10 minus 5 kilogram per meter second. The results are stated as below. And then for the experiment 2B, rough surface flat plate where the initial head is 278 mm. First plate distance is in millimeter is set at 0, 20, 40, 60, 80, 100, 122, and 140. Where the boundary layer thickness in millimeter is counted by 4, 8, 12, 16, 20, 24, 20, and 32. The head H1 is and mm is found as the table in the video. Then, same as the smooth one, we calculate the velocity using the formula, and then we get the velocity here from 0 to 140 in plate distance and 4 to 32 in boundary layer thickness. And then we calculated Reynolds number using the same formula as the previous one, and then we get the result for the second experiment. Then this one is graph for smooth and rough surface forehead, where the orange one represented the rough surface flat plate and the blue line indicates the smooth surface flat plate. The second graph is for the velocity, where we can clearly see that the smooth one has more velocity than the rough surface flat plate. And then for the Reynolds number, in 4 millimeter thickness, there is a different gap, but from 24 to 28 millimeter thickness to 30, we can see that they are getting the same number as they are going together. Now, we will go to the discussion section. First question. Haris, can you explain about the boundary layer thickness in the boundary layer of both surfaces?
Thanks to Mr. Ashraf, I will answer about about this question. Okay. Explain about the boundary layer thickness in the boundary layer of the both surface. The distance between the solid body and the point where the viscous flow velocity is 99% of the free flow velocity is commonly used to define the thickness of the velocity boundary layer in viscid flow surface velocity. We can see from this experiment that the raw surface turbulent region occur at the lower Reynolds number, whereas the smooth surface turbulent area occur at the higher Reynolds number.
Okay, thank you for answering the first question. The second one, what is the distance between in the plate before the flow become turbulent? What phenomena could be the reason of this change?
Okay, for this question, we using a fundamental Reynolds value, we can establish if the regime is laminar or turbulent. This shift occur at the plate distance increase because the region of the viscous layer change and the leaking effect is only important in this area, causing the flow to be disturbed. Okay. To transition from laminar to turbulent flow, the crucial Reynolds number must be achieved. The flow will be turbulent if the compute Reynolds number is greater than the critical Reynolds number.
Okay, now for the third question and the last question, what are the difference in terms of result for smooth and raw surface?
Okay, for the last one, the roughness of the rough surface is greater than that of the smooth surface. As a result, the flow velocity on the smooth surface is higher than the flow velocity on the rough surface at a boundary layer thickness of 16 mm. Thanks to Mr. Acha. Thank you. That's all from me.
Assalamualaikum. My name is Muhammad Azharuddin Muhammad Nawawi. Now I would like to present to you about chapter 5, conclusion. In this experiment, we have finished design complete measurement technique for the fluid flow and the measure of the drag forces applied on the symmetrical aerofoil at the different angle of the tank. We'll also determine that velocity distribution for flat split boundary layer on the plane is generally affected by some factors, such as split flow, Reynolds number, and the roughness of the surface. If the speed flowing fluid is increased, the Reynolds number is also increased. From the experiment we have done, we conclude that the surface roughness has an impact on the boundary layer as well as the Reynolds number, as I said. The thicker the boundary layer, the rougher the surface, and the lower the Reynolds number will be. It can also have a more expanded thickness if run in expansion because the greater shear stress prevalent on the describable surface. The boundary layer will thicken and the liquid stream velocity will decrease when this calculation is increased. Because the Reynolds number is proportional to the liquid stream speed, it will decrease as flow speed decreases. Lastly, based on the experiment result, we have determined that the boundary layer thickness of the plate, subjected to the longitudinal flow for rough and smooth surface, which is the speed of the flowing fluid is much higher for small and for smooth surface plate compared to the rough surface plate.